Hello everybody, this is the next video, and I'm going to read Napier's documentation on how he figured this out and try to explain it geometrically to the best of my ability, because it's very vague and it's also in Latin. It comes from this book that Napier published after he discovered logarithms. It's 90 pages of logarithms, a bunch of other geometry, a bunch of words, a bunch of proofs, and its name is Modifici Logarithmium Canonis Descriptio. And this is, he just gave one blurb of text explaining how he came to the conclusion that you can have a logarithm table and multiply one side and get the result of that multiplication by adding the other side. Quote, and this is a translation from the Latin: one point moves at a constant speed along a line. Quote, another point moves along another line in a way that its distance decreases proportionally to its remaining distance from a fixed point. And this is how I interpreted that. So, there's one line of fixed length, and there's another line of infinite length. The first line and the second line are connected. There are two particles, and they both go the same speed along these lines, and each particle is an increment of time. So, let's say that this line is 1 unit long. We'll say a meter long. And we have a particle that goes half a meter per second. So this is a halfway mark, and the particle on line A travels 1/2 of a meter in that second. On line B, that same particle, or technically the particle in the second line, travels 1/2 a meter in that second. On line A, the distance of that particle decreases proportionally to its remaining distance from a fixed point. So how I interpreted it is, whatever percentage across this line it went, it goes that percentage again. So it went halfway this time, so it's going to go halfway across this line again. And this line B moves at a constant speed along the infinite line. So it goes 1/2 a meter again in that second. On the third second, it goes halfway again, and this goes 1/2 a meter. Halfway, 1/2 a meter. So I created a table based on this. Like Napier supposedly did, where on one side he has a number. He used Greek, so he called it the arithmos. And on the other side, he called it the logos arithmos, or logos, which means ratio, and arithmos, which means number, like right there. That arithmos means number. He concatenated the two words. He called it the logarithm. And over here, what I thought he had for the logarithm, which was actually incorrect. Over here, let's start with just particle 1, 0.5, 1, 1.5, 2, over here, he goes halfway, and then he adds another half, so half of that is an extra fourth, so he goes 0.5, then 0.75, then 0.75 plus an eighth, so 0.875, and then he goes a 16th, so 0.9375. I tried multiplying this side, and it doesn't correspond with the number over here, arithmos, and that's because I interpret it incorrectly. What Napier actually measured was the distance to the end up here, and from here he measured the distance from the start. So actually, it goes 0.5, 0.25, aka a half, a quarter, 0.125, an eighth, 0.0625, for a 16th, I believe. Yes. And a 32nd, so 0.03125. And I don't know how he came to this conclusion, but Napier figured out that if you multiply, for example, 0.5 times 0.25, if you add the values of arithmos, the number, then at 1.5, you'll find the sum, or the product of that multiplication. And it works for every number on here. So let's say we want to multiply 0.5, 0.5 times 0.125. Well, 0.5's number is 0.5, and 0.125's number is 1.5. So 0.5 plus 1.5 equals 2. 2 is 0.0625. So the result, the product of 0.5 times 0.125 should be 0.0625. And if we multiply 0.5 by 0.125, you'll notice that the result is correct. The product is correct. But there is something weird about Napier's logarithm table. It doesn't have any decimal points. And the reason why I realize is because even though it's decimal point accurate here, when you use a different ratio, like let's say, I'll pull it up. if your particles are going 10 meters per second and the length of the fixed line is 100 meters, well, it would end up looking like this. So our blue points are the points on line A, the red points are the points on line B. And I actually went through the effort to calculate it when I assumed that was the distance from the start and not from the end. I just found that I could still use this to graph this. However, with the actual equation, the actual values, at point 0 or at time 0, start at 100 meters from the end, now go to 90 meters because it's going 10 meters per second. Over that distance, it travels a tenth, so it keeps multiplying it by a tenth. So, after that, it would be 81 meters from the end, then 72.9 meters from the end. And if you do math with these, let's say you want to multiply 90 and 72.9. The corresponding arithmos values are 1 and 3. 1 plus 3 is 4. At 4, the result is 65.61. The actual product of 90 and 72.9 is 6,561. Those are the same numbers, but they're not accurate to the decimal place.